Ja, guten Abend, meine Damen und Herren. Wir freuen uns sehr, dass Sie trotz Regen und starkem Wind den Weg hierher gefunden haben, wo es heute Abend eben um Astronomie und Fotografie gehen wird, im Rahmen unserer Reihe Fotografie und Wissenschaft. Vielleicht ganz kurz was zum Ablauf, weil der heute ein kleines bisschen anders ist als die sonstigen Male. Ich werde zunächst ganz kurz die beiden Gäste und Dialogpartner des heutigen Abends kurz vorstellen. Dann wird Herr Starling sein Werk präsentieren, also wird schon mal in das Werk einführen, weil dann im Anschluss eben der Film Black Drop von ihm gezeigt wird. Und da ist es ganz gut, wenn Sie da eben auch schon entsprechend eine Werkeinführung haben. Wir schauen dann, wie es um 18 Uhr aussieht, ob noch viele sozusagen noch externe Leute dazukommen, die dann den Film noch nicht gesehen haben. Dann würde ich für die vielleicht noch mal ganz kurz die wichtigsten Dinge resümieren und dann würden wir in das Gespräch zwischen Simon Starling und Joachim Wambsganß einsteigen. Wie immer ca. 45 Minuten. In den letzten 15 Minuten haben Sie dann die Gelegenheit, auch noch Fragen zu stellen. Mein Name ist Henrik Kiesor, ich bin vom Institut für Europäische Kunstgeschichte. Wir haben diese Dialogreihe ja zusammen organisiert mit der Biennale und eben dem Deutsch-Amerikanischen Institut. Ich fange wie immer in alphabetischer Reihenfolge an mit Simon Starling, geboren 1967 in Epsom in Surrey in England. Er lebt in Kopenhagen und er hat studiert an der renommierten Glasgow School of Art, wo er auch seinen Abschluss gemacht hat. Und er hat dann im Anschluss an diesen Abschluss erst einmal an Museen und Galerien in Schottland als Fotograf zur Dokumentation der Sammlungen und Ausstellungen dort gearbeitet. Und das prägt auch einen wesentlichen Teil seines Œuvres, wie Sie sehen werden, weil es da sehr oft um Sammlungen und Ausstellungen, aber eben um deren entsprechende fotografische Aufarbeitung gehen wird. Er war dann 2003 bis 2013 Professor für Kunst an der Städelschule in Frankfurt. Ich hatte es ja schon angedeutet, dass er in seinem Werk eine sehr breite Palette hat, und zwar nicht nur was die Themen angeht, sondern eben auch was in gewisser Weise auch die Materialien angeht, mit denen er arbeitet. Er wird Ihnen das gleich auch selber noch einmal vorstellen. Ich will vielleicht nur ein paar Dinge vorausgreifen. Es gibt bei ihm eine breite Bandbreite an Medien, mit denen er arbeitet, und er arbeitet eben auch mit den Formen der Installation und der Fotografie und bringt dabei eben diese drei Elemente auch zueinander in Beziehung. Ich will Ihnen vielleicht nur ein Beispiel bringen, vielleicht wird er das gleich auch selber in seiner Vorstellung noch einmal anführen. Er hat 2007 für das Museum Volkwang in Essen nach Fotografien von Albert Renger-Patsch hat er einen Ausstellungsraum aus den frühen 1930er Jahren praktisch rekonstruiert, also sozusagen nachgebaut, hat ihn mit originalen Ausstellungsstücken bzw. mit originalgetreuen fotografischen Reproduktionen dann ausgestattet. Und da sehen Sie, wie das alles zusammenkommt. Also zum einen die Sammlung, die Rekonstruktion von Dingen, das Dokumentieren, aber eben dann natürlich auch der Aspekt der Fotografie. Und in gewisser Weise wird das auch auf den Film Black Drop heute Abend passen, weil es hier ja darum geht, dass Simon Starling eben die Idee zum Ausgangspunkt nimmt, dass der Transit der Venus 2012 möglicherweise der letzte gewesen ist, der auf Zelluloid festgehalten werden kann. Denn das nächste Mal zieht die Venus dann im Jahre 2117 vor der Sonne vorbei. Und Simon Starling ist deshalb eben nicht nur an historische Beobachtungsorte gereist, von denen Expeditionen überliefert sind, wie Point Venus, Tahiti 1769 oder Honolulu 1874, sondern er hat das Naturschauspiel auch selbst noch einmal sehr aufwendig gefilmt und präsentiert uns dieses Material jetzt aber in gewisser Weise sozusagen von der Perspektive jemanden, der an einem Schneidetisch sitzt und jetzt eben dieses fotografische Material sichtet, sortiert und schneidet, um diesem Material Struktur und Ordnung zu geben. Das heißt, hier wird dann also auch mit Material gearbeitet, das aus Archiven und Sammlungen kommt. Und da sehen Sie wieder, wie diese drei Elemente zusammenkommen. Aber wie gesagt, er wird Ihnen das gleich selbst vorstellen. Vielleicht noch kurz etwas auch zu seiner Rezeption. Er hat 2003 auf der Biennale von Venedig Schottland repräsentiert, war dann 2004 auf der Shortlist des Hugo Boss Prize und hat dann 2005 den renommierten Turner Prize gewonnen. Das heißt, also durchaus eben eine respektable Rezeption, die er hier auch erfahren hat. Sein Gesprächspartner heute Abend wird sein Joachim Wambsganß, geboren 1961 in Landau in der Pfalz. Er ist Professor an der Fakultät für Physik und Astronomie der Universität Heidelberg und Direktor des Astronomischen Recheninstituts sowie stellvertretender Direktor des Zentrums für Astronomie der Universität Heidelberg. Und Sie werden gleich sehen, dass er auch einen gewissen Zugang zur Fotografie hat, zu der Art und Weise, wie Objekte aufgenommen werden können. Er hat 1981 bis 1987 Astronomie und Physik in Heidelberg, München und Princeton studiert und hat dann eine Dissertation geschrieben über den sogenannten Mikrolinseneffekt. Das wird er Ihnen wahrscheinlich besser darstellen können als ich. Ich will nur ganz kurz umreißen, worum es da ganz grob geht. Es geht um Gravitationslinsen und deren Effekt ist nämlich, dass in der Astronomie die Ablenkung von Licht durch große Massen eben mit diesem Gravitationslinseneffekt bezeichnet wird. Und Herr Wambsganß hat sich jetzt beschäftigt mit dem Mikrolinseneffekt. Das heißt, es geht hier um den Abstand zwischen den verschiedenen durch die Gravitationslinse erzeugten Bildern eines Hintergrundobjektes. Und eben dieser Abstand wird dann so gering, dass er von den heutigen Teleskopen nicht getrennt beobachtet werden kann und auch die Lichtablenkung nicht gemessen werden kann. Herr Wambsganß war dann 1990 bis 1992 an der Princeton University, hat dann am Max-Planck-Institut für Astrophysik in Garching sowie am Astrophysikalischen Institut in Potsdam geforscht und wurde dann 1999 Professor an der Universität in Potsdam, wurde dann 2004 an die Universität Heidelberg berufen, hat dann zwischendurch noch Visiting Professorships gehabt und es wurde ihm dann eben auch die Schrödinger Gastprofessur am Pauli Center for Theoretical Physics in Zürich zuerkannt, die von der ETH und der Universität Zürich getragen wird. Die Forschungsthemen von Herrn Wambsganß sind Kosmologie, der Gravitationslinseneffekt, extrasolare Planeten, Big Data, virtuelles Observatorium. Vor allen Dingen aber ist er sehr engagiert in sogenannten Public Outreach. Das heißt, es geht ihm also auch sehr stark darum, die Inhalte seiner Wissenschaft auch an ein breites Publikum heranzutragen. Er ist dafür auch ausgezeichnet worden mit dem Werner- und Inge-Grüter-Preis für Wissenschaftsvermittlung oder auch dem Georg-Kerschensteiner-Preis der Deutschen Physikalischen Gesellschaft. Einige von Ihnen werden zumindest eine Institution kennen, die er eingeführt und erfunden hat, nämlich die akademische Mittagspause in der Peterskirche. Die hat nämlich begonnen als Universum für alle, halbe Heidelberger Sternstunden im Sommersemester 2011, wo es also Vorträge, Videos und dann eben auch eine Buchpublikation dazu gab. Und aktuell ist Herr Wambsganß auch Präsident der Astronomischen Gesellschaft. We will now switch to the presentation of Simon Starling, who will introduce us into his work, and we will then continue with the film Black Drop. Please take the stage. Thank you.
How do we turn the lights down again? I've forgotten already. Sorry.
Okay, do we need some?
Oh, that's good.
Okay.
Thank you for coming. I'm just gonna talk for 15 minutes or so before I show the film Black Drop, to try and kind of, I suppose, give some sense of how it came about. I'm not a filmmaker, and I'm certainly not an astronomer. So you might be asking, why did this man make a film about astronomy? And it's probably because it's only partly about astronomy, I would say. And I'm going to try and kind of expand on that a little bit. I was rooting around in my files of images, and I found this picture that we made on a solidified lava flow in Hawaii when we were filming in 2012. We went to Hawaii to film the transit of Venus there from the top of Mauna Kea. And the idea of this kind of moving image device sitting on top of this solidified former river of lava seemed to be a kind of interesting image. And I also found a photograph I'd used before in a talk by Timothy O'Sullivan, who was one of these kind of very courageous, pioneering photographers who went and photographed the US often for the first time back in the 19th century. And he had this huge plate camera and consequently very long exposures. And whenever he photographed rivers, they became more like a kind of, I don't know, gaseous mass or sort of smoke almost. And somehow the two images seemed to introduce some thoughts about the relationship between still images and moving images. And sort of further to that, my interest in filmmaking as an artist. I began my sort of life as a maker of visual images quite young. I built a small darkroom in a little shed on the side of my parents' house when I was about 11 or 12 years old, and started making very bad black and white prints in there. And so photography has always been a kind of, and very much the sort of chemistry-based, silver-based form of photography has been a kind of very important thing for me as a visual artist. And it wasn't until sort of later in life that I started to think about using film and moving image. And I think that in a way, all of the films that I've made, including Blackdrop, which I'm going to show you later, are films that sort of unpack the mechanisms of filmmaking in a way. They interrogate their own medium, or in part they do that, I would say. And this is one of my first forays into the film world, which is it's a work called Wilhelm Noack OHG, and it's the title is the name of a company of metal fabricators in Berlin, who worked in the city for over 100 years. They sadly closed a few years ago, and I made a short 4-minute long film sort of about the company and their history, sort of activating their archive of photographs and plans and documents, and also activating the machinery in the workshops to film with this rather large, solid 35mm camera. And the idea came very fast to invite Wilhelm Noack, the company, to fabricate a loop machine to project the film. And so we came up with this design, which is sort of based on a spiral staircase, actually, to transport the film from the top of the projector to the bottom, or rather from the bottom of the projector to the top. So the 4 minutes of 35mm film run through the projector. And what that does is it sort of puts the film, the individual frames of the film on display in a way. So you have this strange, if you start to concentrate on one point on the ever-moving strips of film, with the flickering light of the projector in the back, you start to see small films happening within the piece as a whole. So it's a sort of strange, almost like a feedback situation that's happening in the projection, and it also sort of it talks to the way in a way that the film was pieced together from a lot of still images, a lot of historical material that's kind of activated with the camera and animated in a way. This is another, briefly just gonna, this is a still from a film called Red Rivers in Search of the Elusive Okapi, which is it kind of conflates two journeys made about 100 years apart. One by me on the Hudson and Hoosick rivers in a canoe, which is what you can see in the photograph there, and the other by a a mammologist who was working for the American Museum of Natural History, and he went on this epic 1909 Congo expedition in order to try and bring back and study okapi, which were living in the Ituri rainforests in the Congo. And the film sort of tells his story through his own words. It's an account, a written account. The voiceover for the film is a written account of his journey into the sort of heart of Africa in search of this elusive creature. But the film is, again, it's constituted largely from still images. The only moving images that are in the film were made in a photographic darkroom under red light. So there's this kind of there's this sense of piecing a film together with still images, and the still images were made by me and a colleague on this journey in the canoe from North Adams in Massachusetts to New York City. And this is one of those still images, us paddling down the Hudson River. And the journey, the visual images culminate in we sort of put the canoe on our heads and walk up through New York City to the Museum of Natural History, and the last images are of the display that was the result of his trip to Lang's trip to the Congo. So again, an example of a film that's very much sort of teasing out this kind of relationship between still and moving images. The last example I was wanting to show was a piece. It's called El Eco. It was made in 2014 in Mexico City, and it's a kind of a contemporary reenactment of a dance that was held in an exhibition space called El Eco, which was developed by the German emigre artist Matthias Göritz, who he wanted to build a kind of art center for a kind of interdisciplinary space where architecture and music and dance and visual arts could all kind of come together and coalesce. And one of the first things he did was he commissioned Henry Moore to make, the British sculptor Henry Moore, to make a large mural on one of the walls in the space. And you can just see the mural in the background behind the glass. And then he invited this very young 15-year-old dancer, Pilar Pellissier, to come and sort of perform in front of the murals. And to cut a very long story short, I sort of tracked down Pilar, who's now a fairly well-known actor in Mexico, and invited her back to try to kind of reconstruct that moment that she experienced as a 15-year-old girl. Of course, with her frail 76-year-old body. So I sort of started out thinking I was going to make a film about Henry Moore and Göritz, but it ended up being a film about getting old, essentially. And then when the film was finished, the film is, again, it's moving image, contemporary moving image, intercut with still images from this 1953, the documentation of her dance performance. And then, of course, the film was then projected back into the space where it was made, just next to the wall where Henry Moore's mural used to be. This is the Red Cliff Observatory, which is in Oxford. And it was It was built following a transit of Venus. In 1769, there was a transit of Venus, which was observed by an astronomer called Thomas Hornsby. And he observed it from another building, the Red Cliff Infirmary, in fact, in Oxford, but sort of pushed the university to build a purpose-built observatory for observing astronomical events. And so when in 2012, the most recent example of a transit of Venus was about to happen, the university thought we need to mark this in some way, celebrate this. So they contacted me through the museum, the Modern Art Oxford in Oxford, and asked if I would be interested in developing a work to mark the occasion of the 2012 transit of Venus. And I mean, as I said at the beginning, I'm not, by any stretch of the imagination, an astronomer. I kind of took the ball and ran with it. It seemed like a really kind of, I don't know, there was something there that fascinated me with this sort of invitation. And I sort of dived into a lot of books, essentially, to try and trace the history of this, the observations of the transit of Venus. And very soon I came across this man with the beard, who, it's a rather bad image, I'm sorry. It's a still, actually, from a film by Louis Lumière, one of the first pieces of moving image. And Janssen is arriving at the Congress of French Photographers in 1895. And he's the first person who gets down the gangplank onto the quay in Lyon to start the conference in the morning. And they showed the film in the afternoon at the conference as a sort of celebration of this. So they processed it and projected it the same day that it was shot. And Janssen was important to my project because he was an astronomer who had a kind of great belief in photography as a tool for science. He's actually, in a way, best known for his extraordinary photographs of sunspots that he made. But he developed, for the 1874 transit of Venus, he developed a chronophotographic device, which you can actually see on the sort of stool stand to the left of the group there. And this device was designed specifically to try and record this very crucial moment in the transit when the black disk of Venus crosses the edge, or the limb, as it's called, of the sun. And this, they hoped, would allow for a very, very precise calculation of the astronomic unit, the distance between the Earth and the sun, which was a very elusive thing even by the 1870s. And this is a drawing of his device. And I suppose what struck me very soon by reading about Janssen was he was also very involved in the world of image making, and he was friends with Etienne Jules Marais, who was developing or subsequently developed similar chronophotographic devices to try and record the movements of bird flight or horses galloping or what have you. And of course he also later in life became friends with the Lumière brothers. And so there was this real sense that what he'd sort of initiated by trying to stop this moment of the transit of Venus precisely was moving image in a way. That wasn't what he was trying to do, but all of that technology evolved out of his kind of thinking about the transit. And just very briefly, the reason that that Janssen believed that the use of photography could kind of help with this calculation of the astronomical unit was that there was this kind of observational sort of oddity that had been observed in previous transit of Venus, whereby the shape of the disk of Venus seems to change shape and distort. It's a phenomenon that became known as the black drop effect, which is where my film's title comes from. And it made the precise calculation of the moment of the beginning and end of that transit very difficult, very elusive. And Janssen believed that if you could make a series of photographs of that moment, then retrospectively you could make a much better assessment of when exactly the transit began. This is another sketch. Those were the drawings made by Captain Cook and his ship's astronomer Charles Green when they observed the transit in Tahiti. This is another sketch of the same thing. Oh, this is a guy who was very, very important to me in making Black Drop. He's a guy called Mike Davies. He's actually an architect who worked for many, many years with Richard Rogers' partners. He was one of the very young team that designed the Pompidou Center in Paris, for example. And he's also a member of the Royal Astronomical Society and the owner of 20 red telescopes. He also only ever dresses in red and has done since the 1970s, and drives a red car and so on and so on. And he also writes with a red pen. And this was our tablecloth from a lunch we had together in London when he was trying to describe for me the workings of various kind of observational techniques. And it turned out that Mike was also going, he's an incredible traveler, and whenever there's a major kind of astronomical event to witness from Earth, he'll travel to the best place to, so he ends up on these little sort of archipelagos in the Pacific Ocean, gazing at eclipses and things like that. And he was also in Hawaii for the 2012 transit of Venus. And then just briefly before we show the film, I just wanted to show some images of its kind of context in the Red Cliff Observatory, which has these beautiful kind of elliptical stairs which go up to the viewing room at the top of the observatory. And this is what people saw when they came to see my film there, which was projected there for a number of months. It actually didn't, of course, coincide with the idea was to have an event when the transit happened. But of course, because I decided to make this film, which involved recording the transit, it was delayed somewhat. So this is the projection of the film, just the moment after the beginning of the transit. One of the sketches that I was showing you of the black drop effect. The lighthouse on the black sand beach in Tahiti, where Captain Cook and his astronomer observed the transit of Venus. And then, of course, a kind of, an image of some observatories inside an observatories, a sort of historical collapse. These are some of the very powerful telescopes which now sit on the top of Mauna Kea, this 4,000 meter high volcano in Hawaii, where we filmed the transit in 2012. So I'm going to now hopefully start the slide. Hang on.
Could you add something to the meaning of the transit of Venus?
Well, indeed I can, and I'd like you to get involved in this a little bit. We saw the movie, but only the pictures moved, and you stayed there, almost unmoving. So I'd like you to move now your hand and your eyes. So I'd like you to stretch one hand, take your index finger up, and then close one eye and then the other eye. And then what you should see is your finger moving left and right compared to the background, like the blackboard or us or something. Okay. So this was meant for you to get some exercise, but this really describes also the method that astronomers used and employed to measure the distance between Earth and Sun. Because with very simple geometry, knowing that your eyes are about 12 centimeters apart, and measuring this angle to be whatever, 11 or 12 degrees, with triangle geometry, you can derive that your finger is about 65 centimeters away. This is called parallax in physics and astronomy in real life. And we learned this in school, and astronomers employ this still to this day. And our brain does this automatically because this is how we do three-dimensional seeing. We automatically see how different things are, because how distant things are, because our eyes see this, do this parallax without us knowing it. Now, back to the Venus and the transit, why it's so important. After Copernicus introduced the heliocentric picture that the sun is in the middle, and then there are the planets, Mercury, Venus, Earth, and so on. And then came Kepler, and then we knew some relations between the distances of the planets, but we didn't know the absolute distances. For example, in the recent nights, you could see Venus very bright in the west in the evening. What some people perceive as a bright star in the evening have perceived this is Venus. And Venus, being the inner planet compared to Earth, is always near the sun, either in the evening after the sunset or in the morning before the sunrise. That's why it's called sometimes evening star or morning star. And with the maximum extension from Venus, again with simple geometry, we can determine how distant Venus is to sun compared to Earth, namely 72% if you do the numbers. But we didn't know what 100% is. And as Simon showed in the film, this is called the Astronomical Unit. This is like 1 meter is for us the unit of length, or a foot or a yard in your country. So this is the unit. And because with this measurement of the passage of Venus in front of the sun, we can do it. But let me explain why this happens so rarely. I've prepared a little model of the solar system. So what you see here is a disk. It's a circular disk. And now just imagine Earth moving around this, the center of this, in 1 year. And at 72% of the radius of Earth, there's Venus radius. And Venus moves around in about 240 days or so. And if you do this to scale, the sun has a diameter of 1.5 millimeters, which is this little thing which you can only see here in the front. So I put this here in the center. And then in the same scale, Earth would be 1/100th of a millimeter, 10 micron, which is less than the tip of this pin here. Earth would be here. And Venus is about the size of the Earth, a little smaller, would be here. Now the problem is, well, you could imagine then, every time Venus passes inside the Earth compared to the sun, we should see it pass in front of the sun. The problem is that this is tilted. This is the orbit of Venus, and the other one is the orbit of the sun, which means we can see Venus in front of the sun only at this very rare instance when Venus and Earth are exactly at this line, which is called the Knotenlinie, the knot. Yeah. And this happens, as I told my daughter yesterday at the phone, 4 times in 240 years. And then she asked me, why do you say 4 times in 240 years and not once in 60 or 61 years? Well, the answer is, it doesn't happen once in 60 or 61 years. It comes in pairs, 8 years apart, and then it takes 105 years until this happens again, or 130 years. So if you add up, in 243 years, it happens exactly twice. Now let me ask you, has any one of you seen the Venus transit in 2012? One? Yeah. In 2004? Yeah, again. Well, sad news to all the rest of you, as Henrik has had told, it happens only in 2117 again. Yeah, so it's tough luck. However, if you're satisfied with the metro transit, which happens more frequently, the next one will happen, I think, in 2031, in 11 years or so. So this is still a very interesting thing, seeing this little dark spot passing in front. Now, this was, well, it happened, as Simon said, in 1631, 1639, but only 2 people noticed it at the time. And then later the academies, the universities, the scholars, they wanted to measure this. And they knew the distance to about 10% or so, but it's as if someone tells you your salary to about 10%, you want to know it exactly. And scientists want to know things exactly. And this is why at these occurrences in the late 19th century, 70 different expeditions were financed by the different academies, the Royal Astronomical Society, others. So this was an enormous amount of money spent by the societies to really measure this. And the problem was, it was difficult. And the reason why they sent these groups to 6 different locations has a number of background reasons. One is the weather could be bad, or the equipment could fail. But the main reason is, and this comes back now to the parallax thing, if I may use the blackboard, you know, I'm a professor. The main reason is, if this is the picture of the sun, then the path of Venus would be something like that. And we learned that this is called first contact, when Venus just touches, and then it's called second contact, when it disappears from the inner part. Then it takes about 7 hours, and here these are contact number 3 and number 4. And now comes the reason why we do this from different locations. If we do it from Hawaii and from Glasgow and from elsewhere, you see a different path, either this or either that. And this was known, of course, to the scientists all along. And Edmund Halley, who's famous for the Halley's Comet, he knew that the next Venus transit would happen 80 years later, so when he was clearly dead. And the reason, at the time, people thought, we just measure, this is called a cylinder in geometry, price and linear. We just measure the distances, and then we know what the separation is. And knowing the separation of the locations on Earth, we can calculate with this geometry thing the distance. It turned out that this was very difficult, and then Halley came up with a smart idea. Let's not measure the angle, which is difficult. Let's measure the time interval from exactly here, from contact 2 to contact 3. Because the green line has a longer duration than the white line, and knowing the durations and knowing the latitude and longitude on Earth, we can measure the astronomical unit. And this is all about the background. And then the problem occurred, this black drop problem. Why we couldn't, or astronomers couldn't really make a sharp measurement at second 3.8 or so, because it was a bit fuzzy or so. Now I stop for the time, and but I can later make a few more additions and comments on that.
Okay. Do you have any questions to Joachim Wambsganß, or because this is essentially a dialogue between two of you. I'm just hosting it.
No.
So.
I suppose I don't know if there is a singular answer to this, but I still, having made this film, I still don't really understand the reason for the black drop effect. Mm-hmm. And it seemed to be there seemed to be many possibilities as to why that was happening. Was it something that of a sort of observational problem that was happening in the observer's mind, or was it to do with gravity? Was it all these? There seem to be many different kind of hypotheses. And is that actually clear now? What the reason for that is?
Well, I think it is clear, but you're absolutely right. Different hypotheses were put forward what it could be. And one would be that it could be the atmosphere of Venus. I mean, Earth has an atmosphere, Venus has a very thick atmosphere, in fact, that it could distort the image close to the sun or so. But Mercury does not have an atmosphere, and Mercury shows the black drop effect as well. So this way people could prove it's not the atmosphere. So what could it be else? After many attempts attempts to explain or so, the answer, as I understand it, is it's an optical effect. All our optics, telescope or glasses, or even our eye here, has a limited resolution. And in this very moment, when the dark disk of Venus separates from the bright border, the optics is just not good enough, not sharp enough to really make a sharp circle. This has also to do with the fact that when we talk about optics, we call it geometric optics. A straight line, a light ray goes this way, and then it's this way. But in fact, light is an electromagnetic wave. It's a wave phenomenon. And when you do optical microscopy, for example, at some point the wave limit enters. And then you cannot just see a sharp boundary anymore. A very sharp image of a point source would be, it would have sort of wavy structure, bright, dark, bright. This is in fact called Airy Disc, after the astronomer Royal Airy, who was involved in these measurements as well, because he discovered it not with respect to the dark drop, the black drop, but in other optical phenomena. And it's interesting, you may try to do it yourself. When you do your thumb and index finger together in front of a bright background, maybe the screen here is bright enough. You either start from separating it, getting very close. The very moment before they touch, it feels like a dark connection. Or when you have it connected, you separate it. You also there's not a clear separation. This is also sort of how you can measure or simulate the black drop with your finger. So, a short answer: it is an optical phenomenon.
Question to you. Why did you make the film in black and white? I mean, these are beautiful images. Is that also sort of a homage to the history of photography, to the history of early movie also? Because I was also very fascinated by the way you showed, for example, the attempt to show images of the moon, which is almost like a prop for a science fiction movie where they model a moon and then they photograph it and say that's the real thing. So was that a sort of homage to the history, or why did you do it in black and white?
I don't know. I think there's probably a lot of answers to that question. I think one of them was this sense of the kind of, the sort of simplicity of the transit as an image. This black dot on a white disk against the black sky, or the void, whatever, and that just seems such a powerful image in terms of its relation to the history of cinema. It's like this idea that the disc of Venus becomes the kind of film which is passing in front of the big bulb at the back of the projector, which is then projecting it on Earth. So, and there was something so sort of fundamental about that as a sort of image production device that it seemed to make sense to me that should be a black and white experience. But I don't know why.
Was it an instant decision, or did it came throughout the development of the project? Did you immediately think this has to be in black and white, or was it something where after a while you decided?
I think it came fairly early on in the. And also, I suppose so much of the image material that we were working with was also black and white. All this archive material, and it seemed. I don't know. It seemed like color would complicate things unnecessarily or something. I don't know.
I thought about it while watching the film as well, and I thought how good that you did it in black and white, because if you would see sort of the street scene in Honolulu in shining colors, it would be very loud, it would jump into your face and make it much less smooth than the way it was. So I like it very much.
And I think you have this, which is related to that, there's this sort of transition from all these different forms of images. There's the contemporary sort of live footage, there's historical images, and there's drawings, and somehow the kind of interface between those things becomes much more fluid if it's all in black and white, I think. And also, I suppose, I just, as I said in the beginning of my little presentation, the sort of black and white darkroom was sort of where everything began for me as a sort of maker of visual images. So I suppose when I started to think about, the film and it was the natural thing to do. Not easy these days, but in 2012 it was a little easier than it is now. But so it's I don't know. It's because as I said before, it's for me it's a film which is as much about making film as it is about astronomy, I think. Trying to, the idea of using the sort of dramaturgy of the editing suite as a way to connect everything, this idea about how you piece together history or a narrative, and all the kind of permutations and sort of, slippages is a kind of word I often use in relation to this. Is sort of, it becomes very clear when you start to see the editor at work, splicing and resplicing and finding the right cuts and so on, the right timings and all of that. So for me there are these two parallel, there's lots of parallel narratives, but trying to make those things. There's so many forms of that kind of slippage embodied in. The black drop is in a way a kind of slippage, a sort of this sort of. It's like they always talk about the decisive moment in photography, but it's like the problem of the backdrop is it becomes an indecisive moment, and then you have Naismith and Carpenter making these kind of sort of sci-fi images of the moon based on what they saw through their telescope and photographed in their back garden, and then published with a completely straight face as being the truth. Yes. And then Captain Cook's death being dramatized and re-dramatized and told and retold, and it sort of runs throughout the whole project, I suppose. This sort of slightly elusive nature of I don't know, truth or something.
Last week we had Joachim Wambsganß here and Benjamin Samuel, and Mr. Wambsganß said that he would like to have economy more put into the audience's conscience, and he was even saying, well, Benjamin Samuel as an artist would have the possibility to do that. Would you see, because you're very much into public outreach, would you see Simon's project as something which also presents astronomy and what it's the heart of astronomy and what the history of astronomy is as a means to bring it closer to the audience?
Absolutely, and I would hope that's why I asked you at the beginning, did you make more films about science or astronomy? Yes, because I feel, life and culture is so rich, it's too bad that some people just focus on one field, whatever art or science or culture or music or sport, so that we should make the transitions for the experts a bit easier, a bit simpler, and having an audience who is interested in film or picture photography getting exposed to such a thing will make them think, I hope, and maybe look up some things. And so I really like this very much. And I do think, in fact, that some science pictures have an aspect of art as well. For example, when you do photographs in the electron microscope with some cells or so, I sometimes think how wonderful these things look. Or, of course, in the heavens, in the sky, some pictures I'm often also awe-inspired when I see this. So I do think there are no natural boundaries between the fields, but just people are often satisfied with what they know. So I very much, I don't know whether this would be called how do we call this, connecting to interdisciplinary or so, or but I like it very much. But I would like to get another connection to between photography, film, and astronomy. But first, let me show you another model. This, of course, is Earth, the blue planet, and in this dimension, the sun would be 750 meters away. And this is, I looked it on Google Maps, is at Peterskirche, where in fact these academic Mittagspause take place. So 750 meters there is the sun, and in this scale it's 7.50 meters high, like the Christmas tree that was put there in Christmas. Now Venus is 72% of the distance, and this is in fact in Märzgasse, where Märzgasse and Landfriedstraße, so put it there. And then imagine that sometimes, twice in 108 years or so, Venus is exactly in front of the sun. Now, getting to Märzgasse brings me back to this photography and science and astronomy connection. In Märzgasse, there's a house where Max Wolf used to live when he was a pupil here in Heidelberg. And he developed an observatory on the top of his parents' house at Märzgasse, and did astronomical observations. This was in the 1870s and 80s. He later studied physics and astronomy, became a professor, and started the observatory, the Landessternwarte on Königstuhl. This was his achievement by, at the time, very rare sponsors. So he didn't use state money, he got private money to do it there. And he was a pioneer in astrophotography, because, as you saw in Simon's film, in the 1860s, 50s, 70s, it took a long time to expose a picture. And you saw this nice still of a river where you describe that the structures look very smooth. So these are exposures of many seconds, and you know some of the wedding pictures of people where they had to stand for 3 minutes like that. Now imagine when you want to take pictures of the night sky of stars, you get much, much, much less light, so you could forget it to first order. But Max Wolf didn't want to forget it. He wanted to take pictures. So he really worked with photographic emulsions, and he worked with the companies. I don't know whether it was Kodak and Agfa already at the time, but they really developed different chemistry or so. So he was one of the first to take really astronomical pictures. And he was the first to take a photographic picture of the Andromeda galaxy. Because up to then, 1910 or so, astronomers just looked through and drew pictures of paintings or so. And only then it was possible. And this was a revolution in astronomy. Because, of course, when you follow the telescope, let the telescope follow the motion of the galaxies or so, you could expose for minutes or hours. And some of the longest exposures today are many, many nights or so, where you can really get deep exposures. So this is really also where evolution of photographic techniques and astronomy science really have a very close connection. And now you mentioned that this 2012 Venus transit might be the last one which was put on film. But I wondered, wasn't this already at the time when a lot of filmers did digital filming? I mean, was it still broad use of...
No. I mean, it was already, in 2012, it was already sort of disappearing.
Exactly.
If anything, it's made a slight recovery since.
Yeah, right, like retro or so. And so I wondered, maybe it was only the one in the late 19th century which were really captured on celluloid in some sense. And this was already a technology in 2004 and 2012, which was at the border of disappearing.
Yeah, sure. Yeah. And I mean, that was again one of the in a way, one of the fundamental sort of motivations for making the film in the first place, this idea of perhaps being the last person to do that. You know, I don't know.
Yeah, and in fact, I know that many photographers and filmmakers hated digital photography at the beginning, and they were very conservative, if I may say so, and we will always do that. And I think by now, probably 97% use digital technology. Well, astronomers hail digital technology because with a CCD on a camera, you would immediately be 10 times or 20 times more sensitive, which means you didn't need to expose for 2 hours, but for 3 minutes or so. And this is why astronomers, together with the military, really push the companies to develop better and better CCDs for astronomy. So in this sense, it might be now a side product that the population at large uses now.
I mentioned the Pan-STARRS.
Indeed, which
camera,
was the largest
which
camera.
Which is digital array.
Did you see it?
No,
it's almost 1 square meter of CCDs. When I was a student in Princeton, you mentioned that the first digital camera was developed, which was a 500 by 500 pixel. And astronomers were so excited with this little digital thing. And now my students have 10 megapixel on their handy camera, and this was a quarter of a megapixel. But now we have gigapixel cameras. There's also one on the Gaia satellite, which was launched by the European Astronomical Society, the European Space Agency, ESA, in 2013. And this is a camera, also 1 square meter, with 1.4 gigapixels. And this satellite measured all stars in the Milky Way over and over again to measure their distance. For exactly, again, this effect, left and right parallax, because this satellite measures it so accurately with about 1/10,000th or 100,000th of an arc second, which is really 2 orders of magnitude better than before, so that we can now measure the distance to all stars in the Milky Way in this triangulation thing with this parallax. And again, the CCD technology is the key to do that.
Yeah. The problem is the volume of data that they produce.
Indeed, but they are very smart people. They really make sure that of this 1 square meter, they put down only less than 1% of the data at any given time. They know exactly where the stars are and do very, very smart technologies.
Those who were present when Tim Rautert was here with Horst Bredekamp, Tim Rautert would be delighted of what you just said, because he said digital photography is not digital photography, it is scanning, it's just measuring of light, and it's not photography.
Well, that's what photography is all about. It's the same. I read this statement, but I don't see the difference. It's just faster and physics rather than chemistry, if you want.
Maybe we make a round table at the very end where we bring together Joachim Wambsganß and Tim Rautert in order to fight it off. So.
I've been making sort of a little bit related. I've been making photographs of paintings recently, a Tiepolo painting in particular recently, and doing that at producing prints at 1-to-1 scale. And to do that, I use a dolly, which is normally used for making moving image, and put a camera on it, and then very precisely move it, maybe 3-4 centimeters each time, and make these kind of slices of images, which are then stitched together. And that way you can get at 300 dpi, which is a good printing resolution, you can get a 1-to-1 scale. But the images are 2 or 3 gigabytes of data every time you want to print one. But it's a very interesting, and again, it sort of relates to what I was talking about at the beginning, this sort of relationship between moving image and still image, and when is a photograph a photograph, and when is it my scanning of that painting is in a way it's closer to making a film than it is to making a still in a way. So it's an interesting kind of area at the moment, I think. This kind of hybrid,
Which Tiepolo painting was that, if I may ask?
Well, it's a Tiepolo painting that was cut into 2 pieces. The big part of it is in Edinburgh, and it's called The Finding of Moses. It's a beautiful painting. And the other part, the smaller part, which was cut away in the 19th century, is in the collection of the Agnelli family in Turin. And it's called The Halberdier in a Landscape. And it's, again, a very very beautiful, but sort of charismatic. You don't really know why it was painted when you see it until you know that it was part of this other painting. So it was just sort of, yes.
You mentioned the Stars Observatory, and this is one of the pioneers in a new development in astronomy, which we call time domain astronomy, but which you would call cinema astronomy, because I try to explain why it takes so long to take pictures in astronomy, and of course the sky is so huge. If you want to take a sharp picture of the whole sky, it takes forever. So, and also people thought in the skies everything's eternal. It doesn't matter whether I take a picture today or tomorrow or in 2 years or in 200 years. But this was just due to our lack of observations on such a short time scale. And the Stars Observatory was already developed to do very many observations of the same part of the sky over and over and over again to see things change. And things that change are positions of objects, of stars, and brightnesses. And a new telescope in Chile is being built called LSST, Large Synoptic Survey Telescope. This one maps the sky every 3 nights completely, so that we really get films of the sky. And we will discover 1 million moving, changing objects every single night. So we will have a database of positions and brightness of things, and then it will be taken another image and then digitally compared, and everything that has changed, either in position or in brightness, will set out an alert to interested astronomers. And then we can use other telescopes to look at this interesting phenomenon. Because if you look frequently enough, everything is like a Christmas tree going on, off, and so on. It's just that up to now we were not in a situation to do it. And now with movies entering astronomy, we are at the edge of opening this time domain.
That's something which is also inspiring your work, technologies, because you were reflecting on technologies in your film. And I read a little bit about your work, and I was especially fascinated by one project which was One Tone 2, where you were dealing with platinum. You used platinum crystals for
platinum salts,
salts,
to make prints.
Yeah, to make prints in order to show how much energy it needs and how much manpower it needs to order to use to produce platinum. So is that something which is interesting for your artworks?
I mean, always it kind of comes. It sort of comes back to this idea of sort of interrogating the means of production in a way. So if it's thinking about the kind of the fundamental sort of mechanisms that you're using to make the work that you're making, and taking that as a sort of subject of the making. So in the case of that project you're talking about, I had when I studied photography back in the late 80s in England, I started making some platinum prints. Because it was it's a very beautiful. You get these very beautiful sort of soft tones, and so it's a kind of a process that died out the beginning of the 20th century, pretty much. And there's a few people who've kind of tried to, modernize it as a process, but it's kind of handcraft. It's really, and so I started just as an experiment to make some prints. And then later, I did a trip to a platinum mine in South Africa to make some photographs of the mine. And one of those photographs was then reproduced with platinum that had been mined in the mine. And I just took a kind of arbitrary, a ton, seemed like a sort of tangible, sort of what a small car weighs or something like that. A ton of ore. How many silver salts can you get out of a ton of ore? And then I made as many prints of the same image of the mine as I could with that amount of platinum. So it's a work that it's somewhere between a sculpture and a series of photographs. You see what I mean? So it's just a kind of so much of the work is sort of trying to sort of get back to the sort of roots of things. I've also been working in the past with, you mentioned electron microscopes, but it's sort of interrogating silver particles from photographs with an electron microscope and building these 3D models of those particles that make up, tiny fragments of an image. I did a project in Massamoka in Massachusetts, which was the town on the eastern side of the US to have the first Chinese migrant workers. A community of Chinese migrant workers were there, and they worked in a shoe factory called the Samson Shoe Factory, and which was just across the road from this old weaving works, which is now this museum for a contemporary art space. And I found this beautiful little stereo image of the Chinese workers standing outside their factory when they were there. They sort of dispersed, and a lot of them went to live in San Francisco, and they had a terrible life. They had to live inside the factory because they were basically scab labor. They were breaking a strike. So I took some silver particles from that picture, and I took them to a lab in Albany in New York State, and we stuck them into an electron microscope, and then sort of went hunting around for some two good-looking particles, but also particles that the strange thing was that so many of them looked like other things. You'd sort of spot a nice one as you went around on this field of gold-plated things, and you'd suddenly realize, oh no, that looks like a horse or something. We can't use that, or that looks like Mickey Mouse, or so we had to find these kind of particles, and then those were there's a program called Spider, which was developed to make three-dimensional computer models of electron microscope images, and we made a 3D model that we then sent to this foundry in China, who make these extraordinary forged stainless steel sculptures, and they made two sort of 3.5 meter long, perfectly shiny blobs, which are the silver particles that I found in the photograph of the Chinese workers. So it's sort of really this idea of really sort of interrogating the and also the kind of the politics and global sort of production systems that surrounded that. It was a moment. Actually, it was in a moment when I went to North Adams for the first time. All I heard was people worrying about China dominating the world. It was in academia, in business. Everybody was having conversations about how do we keep up with China? And it just seemed like a very interesting moment to talk to that. Sorry, I'm banging on. Yeah. So are you using photography in your work in any way? Or?
Well, yes, we do. And I'm also active in this time domain astronomy business. I told you we don't need 8-meter telescopes, but we do 1 or 2 meter telescopes, which are already big enough. And you, Enrique, mentioned it at the beginning. We use an effect introduced by Einstein called gravitational microlensing. That a star deflects light rays, and we see the combined light, and because the star that deflects the light rays passes in front of the background star, we see the background star getting brighter and fainter again. So we really need films like that.
Yeah.
And the interesting part is now when the star passing between is not an isolated star, but a star with a planet. And we search for these planets. And this is a very rare event, roughly as rare as lotto win in Germany, 1 to 10 million or so. But then you have to measure 10 million stars every night, and then you find the win. And so this is what we do. And this is also completely digitized without digital science, it wouldn't be possible because we have a template and then we just compare every night with a new one and do a digital subtraction. I was reminded when I was a little child, the Apotheker Zeitung had always two little pictures, find the 10 differences between left and right, and this is what I did when I was 8, and now I'm 58, I do the same thing. Highly.
So it's actually very closely related to a transit of Venus, no?
Yeah,
in a way.
In a way, it is.
Yeah.
Indeed. Mm-hmm.
Yeah.
Good, so I would say we open now up the questions for the audience. You can ask in German or in English. If you ask in German, we will translate, but you can of course also ask in French or in English or in Italian. We will all translate this.
Well, yeah, but the chips are just getting bigger, aren't they?
Well,
in a way.
The very first chips were already much better than any chemical photoemulsion in terms of how sensitive to light.
Yeah.
So the best chips now take 97% or 95% of the light, and these photographic emulsions used 3% or 4%. And furthermore, they were not linear. With twice the light or 5 times the light, it would not be fine. So this is another advantage of the digital devices. They get linear with the light. Yeah. But as you said, and as I said before, originally these chips were very small. Yeah. So either you could view only a very small angle, like whatever, your thumbnail from here, or you did use a big thing, but then you had your face on 1 pixel. So, and only in the following years, after the very first one, people could do big arrays of these things. And as I said, in every modern handy camera, there are now 10 million pixels or 50 million pixels, and even amateur cameras have 35 million pixels, and professionals probably 100 million, and astronomical cameras have 2 billion pixels. So I think by now, from a technical point of view, the digital photography is by far better than any chemistry-based photography. But of course, it's our emotions and history, and you have other possibilities with a conventional photography.
There's an aesthetic question, I guess. I always wondered if there was going to be some moment where chips would start to be, I don't know, made in a way that was closer to the way film, so that chips would be sort of grown rather than manufactured. Do you see what I mean? That there could be a kind of a hybrid technology that would somehow bring together all of the best things in a piece of photographic film, you know. And part of the great thing about photographic film is when you look at it under an electron microscope, you realize how it's every single particle is completely different from the one next to it. It's sort of
how grainy.
It's endlessly, you know, endlessly varied, and that's why you get this beautiful quality which you don't get from a rudimentary digital camera. And my dream was that you could sort of grow a chip for a camera or something, that it could happen in an organic way rather than, you know, it's just, you know, I don't know if there's people thinking about those things, but...
Well, I think I know what you mean. The CCD chips in modern cameras are all like a square array, like a Rechenheft in third, exactly square. Yeah. And this is, of course, less romantic than everything slightly different. But of course, you could artificially make the pixels different form. But I don't think that we should introduce romantic this way.
No.
Because
at least unfortunately.
Yeah, exactly. Well, you can imagine a mosaic with little stones, either made of only little squares or of little shapes of different size. And this is exactly the difference between digital photography and conventional photography, with all different size and different shapes and so on. Mm-hmm. This is, of course, a different character. So I'm not saying one is better. It's just different.
Yeah. I mean, I still use a conventional film camera. I have an 8x10 plate camera which takes big sheets of film, and I process them in a darkroom. But so much of the work I do is a kind of hybrid thing now, that I make a photograph on my 8x10 camera. I'll then scan that photograph and produce a digital version of it, and then perhaps maybe I don't know, for want of argument, combine that with another scan that I've made, and then I can output that on a machine that prints onto conventional photographic paper, but it's doing it from a digital file rather than from the original negative. Yeah. So there's this constant, and I love that world, this kind of flick-flack between these two realms, which is at the moment, an exciting sort of space. And even today, we watched a film that was made on celluloid and projected on a digital. There were pixels there in front of the film grain.
And it was an MPEG-3 or something on your computer.
Yeah.
Jasmin Meinecke?
Well, first of all, you could see this even in the film. At the beginning and at the end, Simon had this little old strips of film where you also could see the dust. So this is, I think, a factor both in film and conventional photography. One way to get rid of it at the past was to take 2 or 3 images of the same thing, and the dust would never be at the same location or so. So this would, Now, in the digital world, one of the problems is that with these big arrays of a billion pixels or so, you always have a few failures. Sometimes it's individual pixels which are just been dark, they are gone wrong, or sometimes full columns or so. Another thing is, even this big camera of Pan-STARRS is 1 square meter, but it's not a coherent 1 square meter array, but it consists of many 2000 by 2000 little chips. So you have to put them together, and you can never put these 2 chips as closely together as the individual pixels, which means there is larger separation in some arrays. So a way to overcome this is to take images of the sky where you shift your camera by a fraction of the width of a pixel, so that you can later digitally again sum them up or so. So yes, there of course are all kinds of problems. Well, this way we solve, in fact, that if we have a circular focal area, we just take what's the chalk? I put it here. I cannot get rid of chalk. We just take arrays that are inscribed so that they never really touch the boundaries. So, and sometimes if you really want to get all information, you put a pixel here and maybe 2 pixels there. So, but then it's never round. So indeed, it's never possible to have the full focal plane completely covered with pixels. This is in some sense the problem of squaring the circle. What is the Quadratur des Kreises in some sense. Well, I didn't really say by the resolution. I said by the optical instrument, because every camera, every telescope, even the human eye, has a lens where something is mapped on something else. And this can be done only to a finite resolution. But you're absolutely right. With a bigger lens, this effect gets smaller. But we cannot get rid of it completely. Yeah.
Is that a mention? No.
I made an exhibition in when was it? November, December, which was in 2 parts. 1 part in Scotland and 1 part in Turin, in Italy. And I have 2 galleries that I work with. One in Glasgow and one in Turin. And when I discovered the story of this Tiepolo painting that had been cut in half, and one bit was in Turin and the other bit was in Edinburgh, I thought this was the perfect thing. And then on top of that, I've had this kind of long interest, having worked in Turin a lot, in the car industry in Turin. And there's a Gianni Agnelli, who was the Fiat boss. He used to drive. He had he was one of the wealthiest men probably the wealthiest man in Italy. He had a huge collection of extraordinary cars, Ferraris, whatever, all custom made for him. But the car that he used to drive around Turin was a completely standard. Well, he changed the color of the seats, I think, but it was pretty much a standard production Fiat 125, not 126, 125. Sorry, which is a regular kind of family car, so it was a kind of it struck me that it was what was going on. There was a sort of masquerade involved in him driving this kind of, this was at a time where there was a lot of industrial disputes with the unions in Turin, and it was a very complicated time politically. And Jeli, he used to go and watch the football at the weekend at Juventus to be with the workers in that way. And he used to drive this humble car around. And that was a kind of, there was this sense of, he was playing a role or what have you. And when I discovered that he owned part of this Tiepolo painting, which is a kind of the exact opposite of that. It's like this very humble biblical story told in sort of 17th century Italian courtly finery, so that everybody's dressed up in their Sunday best, and there's beautiful greyhounds and dwarfs, and even the soldiers, the halberdiers, they're in incredible finery, and so there was this, I don't know, this kind of nice thing started to, and so I thought, okay, so we have these two parts of the painting in two towns, so why not take? So we found a Fiat 125, the same blue that Agnelli drove, and we cut it into two pieces in exactly the same proportion that the painting was cut. So the big part of the car went with the small part of the painting in Glasgow, and the big part of the painting went with the small part of the car in Turin. So that was the, yeah.
You didn't have that in your exhibition, did you?
That was the end of the story. Ja.
Ja, weitere Fragen von Ihrer Seite?
I think they were, actually I remember one of the astronomers from Oxford University who came to the opening of we had a special screening for people from the university up in this beautiful room in the observatory, and I think he was kind of he came up to me afterwards and said, I think it was absolutely not what he expected it to be, but in a totally positive way. What I think he was completely surprised how, in a way, how sort of conventional it is as a piece of, scientific history in a way. Although there's all these different layers, and there's sort of parallel narratives going on about film and making film and telling stories and all this. I think he was really happy that I'd made something that was an instrument for, what his interests in a way. And that was really nice to have that response, that it was, it kind of, I sort of, it's a weird thing, because in a way, perhaps in the art world, that kind of approach would be considered, deeply unfashionable in a way. But somehow I was very happy that I'd sort of made something that really appealed to the scientific community, that they could relate to and sort of get on board with, as it were. So it went down well, I think. And it's very, I mean, it was very lovely to project it in that room, with these shutters that closed, and there's so many echoes in the film of that kind of space that all these small improvised observatories that they built in Hawaii that you see, and all these kind of things. They're all they all have a kind of a sort of genetic link back to the Red Cliff Observatory in a way, you know, as a sort of, it's a sort of ground zero of some kind in terms of that. So it felt good somehow. Yeah. I wish it could have stayed there in a way.
You made an exhibition on astronomy in the university library a few years ago.
That's right.
That did what Simon just talked about, the way knowledge is produced or truth is produced. Is that something which is important for the history of astronomy if you do an exhibition on that, or would you say no, it's not so important because we deal with objective facts?
No, it's very important, the process of gaining knowledge. And also, as you described in your film, that some astronomers who had very good telescopes to watch the moon then did completely wrong conclusions. And I don't know, I in fact didn't understand, did they sell it as this is how the moon looks, or did they say this is how we think the moon looks?
No, they said this is how it looks.
But this is wrong, of course.
Yeah.
And of course we encounter this occasionally nowadays as well, that some people are so convinced by their ideas that they think this is the truth, but it's just their view of the truth. So there is probably no absolute truth. It's always filtered through our eyes, our brains, our telescopes. And yes, I'm very much interested in this process of how knowledge is.
And in some ways, each kind of step forward in the development of, you know, technology and tools that you're using sort of inevitably sort of forces you to completely, it sort of undermines almost everything that's come before in some way, no? Or there's this sense of you're constantly throwing into question the sort of fundamentals of what we think we know, or something. Even down to the fact that do we believe the tools do we believe the tools we're using? Are they do we believe it, or do we believe that our observing of these things isn't changing those things? Or, you know, there's so many kind of questions around.
And then sometimes it's not the scientific method that decides something is better knowledge than the other, but sort of pure power of whatever fame of the church or authorities. To give you one example again, we all know that Columbus discovered America in 1492 because he wanted to go to India, but the other way. And the reason why he did this was that in the 15th century, astronomers thought the circumference of Earth is 28,000 kilometers. But already 1,500 years before, with the ancient Greeks and Romans, they knew that the circumference of Earth is about 40,000. So they just thought, because this is new knowledge, it must be better knowledge. It was worse knowledge. On the other hand, based on that knowledge, we discovered America, or he. It would have probably discovered a few decades later as well, but not this way, in the intention to get to India the other way around.
Ja, wenn Sie keine weiteren Fragen mehr haben, dann kommen wir zum Schluss des heutigen Gesprächs. Ich möchte mich nochmal ganz herzlich bedanken bei Starling und Joachim Wambsganß.